it's still morning, so good morning, everyone. My name is Divas, and I'm a PhD student at Department of Industrial Engineering at USF, and I'll be taking over from here. So the agenda for this section would be, we named it as Intermediate Data Science with Python. Okay, before saying that, so is everyone audible? I mean, can you guys hear me?
Yes, we can hear you.
Yes.
Okay. So the agenda for this particular presentation will be briefly talking about how to handle data in Python. So that can be importing data in Python, cleaning and exploring the data with data visualization with Matplotlib, and some supervised, as Somit mentioned, some supervised machine learning models. So we will be going over three of those models. The first one is logistic regression using scikit-learn, decision tree model using scikit-learn, and ensemble models using scikit-learn. So for any data science based project, I mean, since the name itself has data, we need to consider some kind of data set for the for the work. And for this particular session, we are considering Amnesty Data Set. And the Amnesty Data Set is a popular data set which has the images of handwritten digits, and it consists of 70,000 data points. And the whole idea with this data point is that given some information about an image or a picture of handwritten image, handwritten digit, we want to we want to develop a model that is able to predict what's written inside that image or what is the letter in that image. So we will be using Amnesty Dataset for the purpose of learning some of these models. Okay, yeah. So these are some packages that are needed that we need to import, and I will be talking about these packages as we move ahead. And whenever we need it, we will just call it and then use it. So let's first import the data point. And if you want, you guys can follow what I'm trying to do. So the easiest way to call the Google Colab is just write Google Colab in Google. I mean, I think you need to be signed in your browser. And once you do that, you can see Google Colab in the top option. Click on Google Colab and create a new notebook. And then you have the Google Colab, then you can simply start writing the codes. So you need to, just to implement the codes, write 1+1, and you can either press this run icon, or you can also use shift and return key, or shift and enter key, and this particular code is executed. So if you guys want, you guys can follow with me. So let's first import the data set. So this data set is already available in Keras. So Keras is one of the popular libraries to implement the machine learning model. So we do not have to go through any pain of uploading the data file to our Google Colab. However, at the end of this session, I will also be discussing how we can actually upload our own data sets that is stored in a CSV file. So for the ease of for saving some time, we are going to use the data file from Keras. So first we need to, from Keras dot datasets, we want to import Amnesty dataset. And once we import a dataset, then we want to divide the dataset into two parts: the training dataset and the testing dataset. So the whole idea behind dividing the data, a huge dataset into training and testing, is that first we want to train our model, or we want to train our model using a huge fraction of dataset, and then we need to, and from the remaining data point that we call as testing data point or test data set, we want to validate how good our model is performing, or we want to check if our model is good enough for actual implementation or not. So let's divide the data set into train and test data sets. So that would be X train, Y train. Okay. Okay. This is the code needed to import that data set. And here, if we see, if we have, divided the train data set into two parts. The first one is X train and Y train. Similarly, we have divided the data point, the test data set into X test and Y test. So here, X means the features of the data points, and Y means the corresponding labeling. So to better understand it, let's say. All the properties of that image of handwritten data points, they are X-train, and the actual labeling or the actual letter that is represented by, that is represented is written as Y-train. Similarly, we have X test for the features and Y test for the labels of test data set. Okay. So after this is done, let's see how our train data, how our data points actually look like. So in order to do that, so let's visualize it. So in order to visualize it, we need to import matplotlib. So matplotlib.pyplot as plt and plt dot show image show, and we want to show xtrain. And let's see how the first element of xtrain looks like. And this is CMap means the color map, and we want our color map to be let's first make it gray and see how it looks like. GRAY gray. So this is how our input data points or the training data sets look like. So we are basically passing a large number of a large number of images like this, and we want to train a model which is able to, say that there is 5 inside this picture. And let's see what other examples of our training data points are. So let's print something that is in 10, and let's make this blue just to see the difference. Okay. So my first data point was 5, and the image of 5, and my 10th or the 11th data point was or is the image of 3, handwritten 3. Now, let's see how our X train and Y train actually look like. So this is how it, how we can visualize it. But if we print X train, it is actually stored in the form of NP array, and whatever somebody explained for almost 2 hours will all be used while, implementing our models. So our input data points, they are stored in the form of NP array. And let's see what is the shape of this NP array. Okay, so out of 70,000 data points that we had, we are considering 60,000 data points for our training, and each data point is represented in a matrix form which has 28 rows and 28 columns. So this is how our training data point looks like. So let's see. And our test, and after we train our model on 60,000 data points, then we want to test how it performs on the remaining 10,000 data points. And the representation of these two data points, these two data sets is exactly the same. Each data point is represented by 28 rows and 28 columns. And okay, so by default, sorry, by default in Keras, out of total 70,000 data points, 60,000 are stored for training, and remaining 10% are stored for testing. But you can always play with that and just, make some changes on the amount of data that you want to train and the amount of data that you want to test on. So I have just kept a piece of code, which I mean we will not be running. I have just kept it so that you guys can know that we can manipulate our train and test data size. So we can specify our train data size to be 0.7. Then it would consider 70% of data points for training and the remaining 30% for testing. So you can manually control the amount of data that you want for training and testing. Okay, so that is good. But there is still one problem with our data set. That is, each data point is represented in a form of matrix. So let's see, X train. Yeah. So each data point is represented in a form of matrix, and there is no way that we can pass whole matrix to the scikit-learn package that we will be using. So in order to deal with this problem, we need to flatten our image, meaning that we need to convert our 28 by 28 matrix into a vector with 784 uh, columns. So the way to do it is simply uh, number of pixels is equals to x train dot set 1 into x train dot set 2. And uh, now we want to modify our x train as the original x train times we want to reshape it. And how do we want to reshape it? Is that we want it to reshape such that train dot set 0 such that we have 60,000 data points and the number of columns in those data points be equals to 784 instead of 28 by 28. And we want to store this in form of as type float. So we do not want it to be stored as integer. We want to store it as a float. And within float, we want to store it as float 32. So there are different bits that we can consider in our computers or in our Python especially. So as you increase the size of bits, so if you go from 32 to 64 bits, the range of data that you can store will keep on increasing. So you can even consider 64 here. I don't think that will create any issues. And similarly, we want to reshape our testing data set. So we want to reshape our test data sets such that we want 10,000 data points, and we want, instead of 28 by 28 matrix, we want to represent that 28 by 28 matrix by 784 columns, a vector with 784 columns. And let's see what it does. Okay, so initially the shape was 60,000 data points, each with 28 rows and 28 columns, and we reshaped our training data set such that we have 60,000 data points, but each data point has 784 columns. And this was just reshaping the data points, so the data set, so that we can implement in our model. After that, now let's talk about logistic regression. So what is a logistic regression? A logistic regression is a parametric supervised learning. This is supervised learning because we have some labels, that is y, and it is parametric because we want to learn, or we want to estimate some of the parameters for classification. And the whole idea behind any kind of machine learning model is the whole aim of any kind of machine learning model is to minimize the error while training. So the way we train our machine learning model is we will always want to minimize our training. So if you want to classify or if you want to predict, so let me briefly discuss the difference between classification and regression. So whenever so let's consider an example where you want to predict the price of house in Tampa. So for the next year. So the price of house in Tampa can take any value. So it can take any continuous value. So it can be 2 million. So it can be 2 million and 1 cent. It can be 2 million and 50 cent, and so on and so forth. So whenever my levels or whenever my prediction are going to take continuous value, then we need to use regression models. And whenever my predictions are categorical. So let's consider a case that we are provided with the images of cats and dogs, and we want to classify them as whether or not they are the image of cat or dog, meaning that we will be interested to classify them in two categories, either cats or dogs, and those are the example of classification. The whole idea with classification is that we are basically categorizing the images or classifying the images, and that's the difference between regression and classification. And logistic regression is one of the easiest and most fundamental technique to do classification. And for our data set, we are going to we want to make a model that is able to identify whether or not whether our image or the handwritten the picture of handwritten letters, they are either from 0 to 10, meaning that they will be either 0 or 1 or 2 or 3 or 4 or 5, 6, 7, 8, and 9. So basically we want to classify them into 10 different categories. That's why we are using logistic regression. And okay, so what do we mean by training? So by training, we want to somehow develop a rule or develop some function that helps us to whenever we input some information, it just gives us gives us our prediction. So we want to train a model. So in the case of logistic regression, we want to estimate the values of theta, and the theta, it comes in this equation, and this equation is called sigmoid equation. So we simply want to estimate the value of theta in this sigmoid equation such that whenever we pass the value of x or our input information, the function gives us some number that ranges between 0 to 1. And based on that number, we want to classify the image, whether it's an image of 0 or 1 or 2, and so on and so forth. So whenever we have two-class classification, the basic thumb rule is that if the output of this sigmoid function is less than 0.5, we classify that image to one of the category. And if the output of this sigmoid function is greater than 0.5, we classify it to the another category. And when we have multi-class classification like we do right now, uh, the value or the limits are adjusted accordingly by the package itself, or we can manually specify. So if we want to code the whole program manually, we can also specify the cutoff value for each of the class. And so this is a complex mathematical function that represents our objective in while training our logistic regression model. So this basically represents the uh, error or the misclassification, and our goal is to minimize it. So the way we can solve, so this is a nonlinear function, and this is a nonlinear optimization problem. So the way we solve this kind of nonlinear optimization problem while training is that we iteratively minimize our error, and after we reach to some convergence point or after we reach to some stopping condition, that is the final value of our unknown parameters theta. So I mean, I don't think it's absolutely necessary for you to remember any of these equations, but simply just to keep it in your mind, there is that even though Python gives us the result pretty fast, the process behind any logistic regression is that we are iteratively updating the value of our estimates, the thetas or the unknowns, such that the final value of theta will give us the best possible accuracy. And yeah, that is how the logistic regression actually works while training. So now let's see how we can easily implement a logistic regression in any kind of data points that we have. So in order to implement a logistic regression, we need to import the package. So the from scikit-learn sklearn dot linear model. Okay, so I mean, as Somvidip said, Python is basically like English language. So all the stuffs that we write here is just identical to talking in English. So from scikit-learn, because scikit-learn is the library which stores all these machine learning models, and from scikit-learn and our logistic regression, it is a linear model, as somebody said in the last presentation. So from scikit-learn dot linear model, we want to import logistic regression, right? So the first step is to import a sorry. Yeah, sklearn.linear underscore model. Okay, so we first step is to import the logistic regression. Then the next thing is that we want to define the model. So let's call our regressor to be logistic regressor. So let's define our model to be logistic regressor, or this variable logistic represents or stores our logistic regression, and we want to use solver is equals to L L B F G S. Okay, so yeah, let me show you how the logistic regression. What are the options that we have within this package? So logistic regression scikit-learn. So if you just Google it, it just directs us to the documentation, and there are so many stuffs that you can control within a logistic regression model. So once you call the model, you can specify the penalty, and this comes with L2, I mean norms and stuffs like that. So let's just ignore this stuff, and there are so many other stuffs that you can control, and the most important stuffs would be solver and max iterate. So like I said, so there are let's see. Okay, so there are one, two, three, four, and five different solvers that you can use. So by solver we mean some algorithms that can solve the nonlinear optimization model and give us the value of thetas, or estimate the values of thetas. So you can choose any of these solvers, and I think the most popular one is, and the most efficient one is LBFGS, and you simply have to choose one of these. And the next is how many iteration do you want that algorithm to run. So the default value is 100, and if your data set is huge, you might want to increase the number of iterations. If your data point is small, you might even want to decrease it just to save the time, and stuff like that. So okay, so for our case, let's just specify the solver as LBFGS and let all other values to be default. So if we do not specify other parameters, then it just considers that everything is default or whatever is set in sklearn. Okay, so we defined our model, that is logistic regression, and the next step would be to fit the logistic regression, fit the training data points in the logistic regression. So that would be logistic, the variable that we define logistic regression with. So you can specify this any name that you want. You can even input your name for the model. I mean, it's fine as long as you call it with the same name everywhere. And just give me, okay, yeah. And we want to fit this model in our training data set, right? X train, comma, y underscore train. Okay, so it is fitting it, and there are multiple iterations going on within this, while we are fitting our training data points. If you had to manually code a logistic regression, it would be a nightmare. But I mean, thanks to Python and advancement in these technologies, everything is in package. So you can simply call the package and then run the models and then get your output. Okay. So it ended the fitting process or the number of iterations. And if you can see, if you, it's always a good habit to read whatever comes in your console. And so Here we can see that we have one warning, that is LBFGS, or the algorithm for solving nonlinear optimization problem. It failed to converge, meaning that we have a really huge data points, and in order to estimate all the estimates to a high level of accuracy, we need to increase the number of iterations and solve it once again. So it says increase the number of iterations, the max it. So our default values of maximum iteration is 100. So we need to increase it to 200, 300, or maybe up to 500, and then resolve the model to avoid this warning. But for the time being, let's assume that our model is correct, and then move ahead. So after we fit our model, then based on that fit, let's predict some of our values and see if it makes sense or not. Predict X test. We simply want to say first, let's see what are our first 10 predictions. 0 to 10. Perfect. So the predictions are, so what it is saying is, for your test data set, your first image that we passed is 7, the second image that we passed is 2, the third image that we passed is 1, the fourth is 0, and so on and so forth. And instead of just testing for 10 data points, let's test it for the whole uh, training data set, the testing data set. Okay, so it did give us the prediction of all of our test data set. But how do we know how is our model performing? So there must be some measure to measure how good our how good our model is performing. So one of that measure is the accuracy score. So let's call it score is equals to logistic regressor dot SUR score X underscore test comma Y score test, and let's print the value of score. Okay, so our mean or the average accuracy of our model was 92.55%, meaning that we trained our data set into we trained our 60,000 data points, and we learned some unknown we learned the parameter theta, and based on that theta, now we are making prediction on the test data set. So once we make the prediction, then we compare how our predicted value looks with the actual y values, and based on that accuracy, the overall accuracy of our model is 92.55%, meaning that out of 100 instances, almost 92 our model can predict the handwritten letters accurately almost for 92 of the instances. However, I mean, although this score is a good measure of our model, but for classification problem, the another measure for performance of our model is confusion matrix, and this is something really important. So let's see how we can create a confusion matrix, and let's see what a confusion matrix means. Confusion matrix is equals to confusion underscore matrix y underscore test comma predictions. Perfect. Matrix. Let's print our result, and it gives us an array. So I think it is really important to understand the concept of confusion matrix. So let's see what it means. So the left hand side of this matrix means the actual values, and the right hand side or the columns of this matrix means the predicted values. So for letter 0, out of all the samples of letter 0, letters that were 0, or the images that had handwritten zeros, we were able to correctly classify them as 0 for 963 of instances, and for three of the other instances, we classified the letter 0 as letter 0, 1, 2, and 3, and for one of the instance we classified letter 0 as 4. And for other 3 instances, we classified letter 0 as 5, and so on and so forth. Similarly, for letter 1, we did not classify any letter 1 as letter 0, and we classified 11 hundredths of letter 1 as letter 1. That means we correctly classified letter 1 for almost 11 hundredths of instances. But for 4 of the instances, we classified, or our model was able to classify, our model classified letter 1 to be letter 0. And for 2 of the instances, our model classified letter 1 to be letter 3, and so on and so forth. So if depending on the need, if you are not satisfied with the result that you have in the confusion matrix, then you might want to, either change some parameters, increase your training data set, or change some parameters in your model, and then rerun the result, rerun the logistic regression model, and then again check your confusion matrix. And if you are not still happy with the result of your logistic regression, or if you are not happy with the confusion matrix of your logistic regression, then you might want to, discard the logistic regression and go on with other models that are available. So that's about logistic regression. And one interesting visualization that I found was, just give me a second. Oh yeah. No. Oh yeah. Okay. You can even plot the confusion matrix. Let's see. So in order to do that, we need to import from scikit-learn.matrix. We need to import plot confusion matrix, and we simply need to pass our model and x test and y test. So this is how your confusion matrix looks like if you visualize it. Let me just do. And if you look at the, I mean, it's a heat map, so it's easy to visualize, unlike the matrix. So the heat map says that if you go to the lighter shades of yellow or green, that means you have larger number, and if you go to the darker shades of blue, it means you have a smaller number. So we can see that our model was able to predict predict accurately almost all the classes, and the most accurately classified class was class 0, or the letters 1. So for letter ones, we were able to classify most of the instances accurately. And that is all for logistic regression. So before moving to other models, I would like to take a moment to take any questions that you guys might have. Anything that you guys want me to repeat or explain it once again, or you guys have any doubts? Okay, perfect. So if that's the case,
Excuse
okay.
me, actually, I have one question. Like, so why did we change the size of the training data set to like two-dimensional data set, two-dimensional matrix, like
Okay.
from three-dimensional to
So Uh, that's a good question. Thank you. And it's because the way these packages are defined, and for this package to work, or the for scikit-learn package to work, our training data sets, it can have the features can be represented only in the form of columns, not a matrix. So just give me a second. Somewhere around here. Okay, yeah. So if we actually visualize these data points, so let's say data point 1 itself has 28 rows and 28 columns. And the package that we have, I mean, or the scikit-learn package that we are trying to use, it is not able to identify or distinguish or understand those kind of data structure. The only way it can understand the data structure is the whole data set should be represented in the form of rows and columns. So this is a multi-dimensional data set, right, which has 3 dimensions. This is not something that scikit-learn understands. So we simply had to convert it into a 2-dimensional data set, something like this. And one of the way to one of the way to deal with images is that we can simply flatten the image, meaning that we can we can change the pixel of the image. So basically here I think we are changing the pixel of the image. by changing the shape of the each image. And that's the reason for us, to change the shape of the training data points. So
Like, thank you. Thanks so much.
did I answer your question?
Yeah,
Thank you so
thank you.
much. Okay, so now let's move to the another method that we have, and that's decision tree. So as we keep on going ahead, I think we keep on moving towards the more advanced methods. So decision tree. So unlike logistic regression, decision tree is not a parametric method. So here we do not estimate any parameters. So back in logistic regression, we had to estimate the values of theta, and our training was just to estimate the value of theta. But in decision tree, we do not estimate any parameters, and it is also a class of supervised learning. So we can use decision trees either for classification or regression depending on the need. And the idea while training the decision tree is the same, that we want to minimize the error, prediction error, or we want to minimize the misclassifications. So this the figure on the left, it represents one of the trained decision tree. So after you train your decision tree, if you visualize it, it would look something like this. So your data points, so for this particular instance, your data point might just have two columns, x1 and x2, or two features, x1 and x2. And how that how a unseen data point will be classified is that it passes from the root node, and we check the condition. Is the value of feature 1 or x1 greater than 0.5? And we get yes or no question. If it is true, or if the answer is yes, then we directly classify it as a red object. And if the answer was no, then we have second or the next checking condition, that is the value of x2 greater than 0.5? And if the answer was no, then we directly classified that object to a blue class. But if the answer was yes, then we were still not able to classify the object. So we had to add one more checking condition, and the checking condition that was added in the training process was, is x1 greater than 0.1? And if the answer was 1, then we classified it as red. If the answer is yes, we classify it as red. And if the answer is no, we classify it as blue. And this is how our trained decision tree looks like. And we can also, for if we have only two classes that we want to classify, then we can simply visualize that decision tree in a form of plot. So in this plot, the x-axis represents x1 or feature 1, and y-axis represents feature 2 or x2. So the decision rules are, if x1 is greater than 0.5, directly classify those objects as red object. And if x1 is less than 0.5, then we need to have one more checking condition. Is x1 okay? Yeah. If x1 is less than 0.5, meaning that we come along this branch, then we need to have one more checking condition. And the checking condition was, is x2 greater than 0.5? So in x2 axis, we again check, is x2 greater than 0.5? Then if the answer is no, then we classify those data points into the blue data points. But if the answer was 1, or if the answer was S, we further need to add one more checking condition, and that's, is x1 greater than 0.5? Is x1 greater than 0.1? Meaning we create one more vertical breaks. And if it answer is true, we classify those data points into red data point, and if we classify the remaining data points into blue data points. And similarly, we have another instance of decision tree, and this is the decision tree for a very popular data set, that is iris data set. And if any one of you have ever thought of reading data science in your own, you guys must have heard about the name of iris data set. I think it's available in scikit-learn, the inbuilt data set in scikit-learn. And this is what the complete decision tree for the iris data set looks like after you train your data set. So the first checking condition was, is the petal length or the petal length of each of the flowers is less than 2.45? And if the answer was true, we directly classify them as class Setosa. If false, we add one more checking condition, and so on and so forth. And one important concept in decision tree is Gini Index. So let's see what Gini Index is. So in root node, how does our while training, how does our model identify which feature to consider? Because there are so many features that can be considered in the iris data set itself. So there are petal length, there are petal width. One of the feature is petal length, one of the feature is petal width, the other feature is sepal length, and so on and so forth. So among these three features, which feature should be selected in the root node, or which feature should be selected for the first checking condition? So in order to do that, the algorithm or the descent tree model, what it does is that it calculates the Gini index for uh, each of the features. So it calculates the Gini index for petal length, for sepal length, and for petal width. And the one with the smallest Gini index is chosen as the checking condition for that particular node. So in this node, the Gini index for petal length less than or equals to 2.45 was the smallest among all other possible choices from the features. So that's why it was chosen here. And when we come here, so how does the model identify that this is the final classification, or that we prune the tree, or that we terminate the any further branching of this node? Is that if the Gini index in this particular node is equals to 0, then the model identifies that this is the terminal node, and we classify all the data points in this no, all the data points that come to this node are classified into one category. So as we keep on going from top to the bottom of the tree, we can notice that the Gini index keeps on decreasing. This is because the proportion of data sets that are already classified keeps on increasing. So by the time we come from first node to second node, we have already classified some of the data points. So since the proportion of remaining data points is small, my Gini index will keep on decreasing as we keep on progressing in the tree. So if you see here, this is 0.5, and if we go down, then it's again 0.16 and 0.425, and keep on decreasing. And the terminal nodes, all of them, they have Gini index 0, 0, 0, 0, 0, 0, 0. And that's how the decision tree model, it identifies the checking condition and the terminal node. And okay, yeah. So before moving ahead, so let's see what are the parameters that we can control in decision tree while we implement this model. Okay, so the parameters are criteria. So one of the criteria to identify the checking condition is Gini index. The other idea is entropy. So I mean, due to that time limitation, I would not like to go into the detailed mathematical representation of these two criteria, but they basically represent the same thing, that is impurity in the data set. And the value of Gini index, it ranges from 0 to 1, while the value of entropy, it ranges from, oh no, I'm sorry, I think it's other way around. The value of Gini index, it ranges from 0 to 0.5, and the value of entropy ranges from 0 to 1, or something like that. And I mean, although the measure can be different, but the idea behind both of these criteria is the same. And the next important criteria or the parameter is maximum depth. So you can control, if you have a really large data point, then it might be computationally challenging for you to create the whole tree. So you can even control how deep you want to go in your tree, meaning that you can even limit your tree up to here and make the prediction based on that. So that is controlled by that is controlled by yeah that is controlled by maximum depth. And mm, yeah, I think those are the important parameters, and the other parameters, it can be found on this particular link in scikit-learn package, or the documentation of scikit-learn. And now let's create a decision tree model for same data set and see how it performs in comparison to the logistic regression. So the first step is that we need to, from sklearn dot tree. So for logistic regression, since it is a linear model, we had sklearn.linear. But in decision tree, it's a tree-based model, so we have sklearn.tree, and we want to import decision tree classifier. And after we import our classifier, then we want to define a model. So let's define it as dt model is equals to decision tree classifier, and let's specify the criterion criterion to be Gini Index, and let's leave everything to be the default value. I mean, we can always come back and update these values if we are not satisfied with the result of our model. But for time being, let's just keep rest of the values to be default values. Then the next step would be to fit our model dt underscore model fit into our training data set. That would be x underscore train and y underscore train. So after we fit this model, then based on the data points, our model, this DT model, will have created a structure something like this, or we'll have we'll have created a rule something like this. And okay, since we did not specify any parameter for maximum length, maximum depth and stuff, it might take a while to run this model as a whole. Okay, this is pretty good. It ran fast. So the good thing about scikit-learn is that it even gives what are the parameters that it set in our decision tree model. So the next step, once we fit the model, the next step would be to predict. So it will be dt underscore model underscore prediction is equals to dt underscore model dot predict, and we want to predict it based on the x test value. So why do we only pass x test value while predicting? Why not the y test value? Anyone who is familiar with this? So while training our model, we pass both x train and y train data points. But while predicting, we just pass x test, even though we have y test. We have created y test somewhere above here, but we are only passing x test. And why is that the case?
Yeah, it's because we want to just quantify our error based on that.
Yes, because we want to measure how our predictions are with the actual values, actual y's, and based on that, we want to quantify our errors, like what you said. So this is our prediction, and after we did our prediction, then we can evaluate our model on two criteria. That first one is the accuracy score, and the second one is the confusion matrix. So let's first print our accuracy score. dt underscore c score is equals to dt underscore model dot seo underscore, and we need to simply pass the xn. X underscore test y underscore test, right? And let's print our dt underscore score. So the accuracy was 88. The accuracy is 88%. So if your measure, so if you do not care about confusion matrix, or if the project that you are working on is such that you do not care about misclassification on individual classes, and you simply care about the overall accuracy, then our decision tree, it performed poor in comparison to our logistic regression. So the accuracy for our logistic regression was almost 92%. So I would choose uh, logistic regression in place of decision tree. However, if we are interested in one if we are interested in the accuracy of one particular class, then we might have want to evaluate decision. We might want to evaluate the confusion matrix before making the decision on the good models among the models that we have. So let's first create the confusion matrix and see how it did. Okay. Model matrix equals to confusion matrix test comma model predictions, and we want to print okay. Now let's just compare it with print dt underscore model underscore. Okay, I forgot what I. Okay, let's make some comparisons with the confusion matrix that we obtained from logistic regression and the confusion matrix that we obtained from decision tree. So using decision tree, the our model was able to classify the images of class 0 for higher instances, for higher number of instances as compared to the decision tree. Similarly, the same thing applies with uh, the images with 1, images with 2, images with 3, 4, 5, 6, 7, 8, and 9. So with this we can see that our logistic regression model was able to classify all the classes or the images with each letters accurately for all the instances as compared to the decision tree as compared to the decision tree model. So I would choose logistic regression for our case. And I also have a piece of code for showing how our decision tree looks like. So let's see if it works. Hmm. Okay. While that runs, we can talk about the advantages of decision tree. So the advantage of the decision tree is it is non-parametric, meaning that we do not have to estimate any parameters. We simply have to find the checking condition or the splitting condition. And the biggest advantage of decision tree is that it is easily interpretable and the trees can be visualized, like something like here. So this is what our actual tree was. This is really big. Okay, let me see if I can find it, the root node. Anyway, so there is some root node, and as we go below the root node, our Gini index, it keeps on decreasing, and at terminal nodes, we have it as the Gini index is 0. And so if you pay attention to these terminal nodes, so anything that comes into this terminal node is classified as letter 8, and anything that comes under this tree, under this node or under this terminal node is classified as letter 8. Anything that comes under this terminal node is classified as letter 98765. And in our training instances, 6 of those cases were classified as letter 5 through this terminal node. And in this, two of the training data points were classified as class or the letter 8 or letter 7 using this terminal node, and so on and so forth. So the biggest advantage is you can visualize the result and you can see if it makes sense or not. And while presenting your model to while presenting your result to any of the business owners, they are not going to understand any hard and fast mathematical formulation or any fancy models. the only simple things that they can understand is figurative representation, and I think decision tree is really good for that purpose. Not the accuracy, but the model visibility and interpretation. And one of the biggest disadvantages of decision tree is that it overfits our data, and it has high variance. Overfit the data means that it keeps on, if we do not set the parameters properly, it keeps on going on till the end of the tree, and our model is uh, our model is trained such that we want to predict the training data set accurately rather than the unseen test data set. And with high variance, we mean that a small variation in our test data set creates a high deviation from expected result. So these two are the biggest limitation of decision tree, and in order to overcome these two limitations, people came with ensemble models, and one of the easiest ensemble model is random forest. So like the name suggests, we want to create a collection of tree to form a forest, and the way we select the trees is random. That's why you got the name random forest. Random selection of tree to create the forest, and that's how it is called as forest. So this is a typical representation of forest with so many trees, and each of the forest it classifies each of the data points while training, and at the end of a training, we derive a thumb rule for classifying based on the majority voting. So let's say we pass one data point, and this tree classified that data point was class 1, this tree classified that data point as class 1, but this tree classified that data point as class 2, and this tree classified that data point as class 3. So among the four trees, the highest number of classification for the single data point was 2 with these two trees. So based on majority voting, we classify that data point to be of class 2, and that is how the bias and variance are reduced using random forest. So I would not like to, I mean, because of time limitation, I would skip this part, and I would directly show you how how we can implement our model. So I have the codes already written, so let's just print it. And so the same way we call the random forest classifier from ensemble models in scikit-learn, then we define our model, and the parameters that can be controlled in, there are so many different parameters that can be controlled in random forest, and one of the critical is number of estimators, meaning that how many trees do you want in your forest. So it can be 50, it can be 100, it can be 1000. And however, I mean, as far from my experience, if you keep on increasing the number of trees, your result will not perform. So after you reach to certain number of trees, so that is most likely below 500 or below something around 200 to 500. So the ideal number of trees in a forest is always going to be between 200 to 500 for any size of data. So if you keep on increasing the number of trees more than 500, I mean, most likely your model will, the performance of your model will only degrade. And based on our created model, we are going to fit the model, make the predictions, and in order to see how our model is predicting, we are going to create the confusion matrix, and we are also going to see the accuracy score, so which one is critical for you. So for this instance, random forest outperforms all the I mean, remaining those two models that we just talked about. So if we want the overall accuracy to be high, random forest has the accuracy of 96%, logistic regression had the accuracy of 92%, and the descent tree had the accuracy of 88%. So I would choose random forest as the model for my actual implementation. And the advantage of random forest are self-tuning, no tuning required, meaning that we do not need to tune that many parameters. So I think the important parameter is the number of tree, and rest of the parameter they are self-tuned, and it helps to control both the bias and variance. That was the biggest issue with decision tree. It is moderately fast, and for a really huge data science project, you can simultaneously train your individual trees in parallel computers and get the result in feasible time. And that's all for these three models that we wanted to talk. We wanted to include neural network as well, but because of the time limitation, we were not able to do so. And I have one more section of codes. So this shows how we can actually upload our own data points in Colab. So from google.colab import files, and we want to upload that file. So if we run this code, it allows us to upload the file. So let's say we want to upload some data points that is in CSV format, and now that is uploaded. So if you simply, there is no way we can use this data set for, our machine learning model. So we need to, make convert this into something that is understandable, and that's where pandas comes into play. So our Amnesty data set, it is a cleaned and pre-processed data set that is readily available and that's easy to implement. But the real life instances of data sets are not going to look like that. So we might have to clean our data points. We might want to understand our data points. So for that purpose, we want to create the data points, transform the data set into a pandas data set. And sorry, should we test. And after you import it as a PDF, pandas file, this is what it looks like. And you can perform so many different operations using pandas. You can print all the column names that we have. You can see how many NaN values are there in a specific column called cabin. So in cabin, we had, out of 418 data points, we had 327 of them were NaN. So I mean, most likely we are going to completely delete this data point while we are considering this data point. Most likely we are going to completely delete this column while we are going to use our machine learning models. And yeah, and you can also drop some of the columns that you don't want in your machine learning model, either because of this a large number of NAs or empty values, or because of because they are not significant to your model. So you can drop it, and your final model will, your data set looks, from this it looks like something like this. So it's really easy to manipulate your data points using pandas. That's why we spent a huge time for this session in the introduction of Python rather than the model itself, because the implementation of model is easy. The difficult part is coding, understanding how to import the data points and everything, and how to interpret the results that we get from the models. And so that's it from my part. So if you guys have any questions regarding the section that I presented, and if you guys have any feedback, I'll be happy to hear those. And he did a really good job throughout the year, and thank you for hosting such a great bootcamp session for this year.
Thank you, Diwa. So thank you to all the attendees for your attendance today. So with this, I think that we are finished with the data bootcamp for the 2021. So we are gonna, well, the last thing that I have to say is that we are gonna share with you the recording of all the sessions that we have, the R session, Power BI session, and this one, the Python session. So thank you one more time, and well, see you in some, I don't know, in some time in the future. Right. Take care.
Thanks. Bye-bye.